A cosmic visitor from beyond our solar system vanished behind the sun on October 29th, 2025. For 3 days, we lost sight of it during the most critical moment of its journey, when it should have been torn apart by solar fury. But when 3I Atlas emerged, it hadn't died. It had transformed. What happened during those invisible hours could rewrite our understanding of interstellar visitors, challenge our assumptions about natural versus artificial objects, and force us to ask whether we're truly alone in witnessing the cosmos or whether the cosmos is witnessing us. NASA's orbital tracking systems flagged non-gravitational acceleration. The European Space Agency documented unexpected brightening. Multiple observatories across 3 continents confirmed something impossible. This object turned blue when physics demanded it turn red. These aren't rumors. These are confirmed measurements from institutions that don't make mistakes lightly. But how does a comet accelerate beyond what gravity allows? Why does it brighten when it should dim? And what really happened during those 3 days when we couldn't watch? Tonight, we descend into the mystery of 3I Atlas, the third confirmed interstellar object ever detected, now active again after passing through fire. Over the next 2 hours, we'll examine the timeline, the measurements, the competing explanations, and the December deadline that will determine whether this remains a curious anomaly or becomes something far more significant. This is science at the edge of understanding. This is where certainty dissolves into wonder. In the entire documented history of human astronomy, spanning telescopes from Galileo's first observations in 1609 to the sophisticated arrays of today, we have confirmed the existence of exactly 3 objects that came to us from beyond our solar system. 3, not 300, not 3,000. 3 visitors in 4 centuries of watching the sky with progressively sharper eyes. And the third one discovered on July 1, 2025 by the Asteroid Terrestrial Impact Last Alert System telescope in Chile, now moves through our cosmic neighborhood with characteristics that challenge what we thought we understood about interstellar wanderers. 3I Atlas carries its designation like a passport from the void. The 3I marks it as the third confirmed interstellar object, following 1I Oumuamua, which slipped through our solar system in 2017 before we fully understood what we were seeing, and 2I Borisov, which arrived in 2019 and behaved almost exactly as our textbooks predicted a comet should behave. But 3I Atlas is teaching us something different. The mathematics of its trajectory tell an unambiguous story. This object follows what astronomers call a hyperbolic orbit, a path with an eccentricity of approximately 6.1. To understand what this means, imagine throwing a ball straight up. On Earth, gravity pulls it back down in a parabolic arc. But if you could throw that ball fast enough to escape Earth's gravity entirely, it would follow a hyperbolic path, never returning. That's 3I Atlas. It came from interstellar space, will swing once through our solar system's inner regions, and will return to the darkness between stars, never to come back. Its origin point, traced backward through celestial mechanics, places its arrival vector in the direction of Sagittarius, near the dense star fields surrounding our galaxy's center. Somewhere out there, perhaps orbiting a star we've catalogued but never studied closely, or perhaps wandering the interstellar medium for millions of years after being ejected from its birth system, this object began a journey that would quite by chance intersect with our sun's gravitational influence. The discovery itself was almost routine. Atlas, designed to detect potentially hazardous near-Earth asteroids, captured an image showing a faint moving object. Within days, follow-up observations confirmed its unusual velocity and trajectory. By mid-July, orbital calculations revealed the hyperbolic path. By August, the astronomical community had designated it 3I Atlas and began coordinating observation campaigns for what everyone knew would be a brief opportunity to study this rare visitor. Current estimates place its diameter somewhere between 1 and 5 kilometers. roughly the size of a small mountain, though uncertainty remains significant. At the speeds it travels, estimating size from brightness measurements becomes complicated. During its approach through October, it was moving at approximately 68 kilometers per second, or about 42 miles per second. At that velocity, you could cross the continental United States in less than a minute. To place this in cosmic context, our solar system moves through the galaxy at roughly 220 kilometers per second as we orbit the Milky Way's center. But that motion is shared by everything gravitationally bound to our sun planets, asteroids, comets formed in our system. 3I to Atlas moves differently. Its velocity vector corrected for the sun's motion shows clearly that it came from elsewhere, carrying with it the momentum of different gravitational histories, different stellar neighborhoods, different formation conditions we can only glimpse through analysis of its composition and behavior. And this is what makes each interstellar visitor so scientifically precious. We cannot yet send spacecraft to other star systems to study their debris fields, their comet populations, their asteroid belts. But occasionally, very rarely, samples from those distant environments come to us. Each one is an interstellar postcard, a message written in ice and rock and the subtle chemistry of materials formed under alien suns. The timeline of 3I Atlas's passage was calculated months in advance. Astronomers knew it would reach Perihelion, its closest approach to the Sun, on October 29, 2025. They knew it would pass approximately 203 million kilometers from our star well inside Mars's orbit, but safely distant from Earth. They knew that observations would be complicated by the object's position relative to the Sun from our viewpoint. And they knew that this would be their only chance to study it in detail before it faded beyond the reach of even our most powerful telescopes. What they didn't know, what no one could have predicted with certainty, was that 3I Atlas would refuse to behave the way physics textbooks suggested it should. The summer observations throughout July, August, and September showed an object following predictions beautifully. Brightness measurements tracked with distance calculations. Spectroscopic observations hinted at water ice and dust standard comet composition. Its trajectory matched gravitational models with the precision we've come to expect after centuries of refining orbital mechanics. Everything appeared normal. But normal is a word that applies only until it doesn't. By early October, as 3I Atlas accelerated inward under the sun's gravitational pull, subtle discrepancies began appearing in the data. Small at first, within measurement uncertainties, the kind of variations that might be dismissed as instrument calibration issues or atmospheric effects if they appeared in isolation. They didn't appear in isolation. Multiple observatories using different instruments operating on different continents began documenting the same phenomena. Brightness changes that didn't quite match predictions, velocity measurements that suggested acceleration beyond what gravity alone could explain, spectral signatures that were almost but not quite what conventional comet models anticipated. And then came October 29th, Perihelion, the moment when 3IR Atlas would experience maximum solar heating, maximum physical stress, and maximum opportunity for direct observation of its response to our star's intensity. Except we couldn't watch. For 3 days, as 3I Atlas swung through its closest approach to the Sun, it passed almost directly behind our star from Earth's perspective. Direct observation became impossible. The most critical phase of its journey occurred behind a solar curtain we couldn't penetrate. What emerged on November 1st when visibility returned was an object that looked different, behaved differently, raised questions that astronomers are still working to answer. This is where we stand now in early November 2025 with an interstellar visitor that survived perihelion passage and now moves outbound through our solar system, accessible to observation for perhaps 6 more weeks before it fades beyond detailed study. What happens during those 6 weeks, what we learn or fail to learn, will determine whether 3I Atlas becomes a footnote in astronomical catalogs or a case study that reshapes our understanding of what's possible. The universe has sent us 3 visitors. Each one teaches different lessons, and the third one, it seems, still has much to teach. There's a particular quality to astronomical observation in the months before an anticipated event. A quiet accumulation of data points, position measurements, spectroscopic readings. Night after night, telescopes across the world point toward the same patch of sky, capturing photons that have traveled millions of kilometers from a small, dark object reflecting sunlight. Each observation adds to the mosaic, refining our understanding incrementally. For 3i Atlas, the summer of 2025 unfolded in precisely this fashion. The European Space Agency's JUICE spacecraft, Jupiter Icy Moons Explorer, diverted a small portion of its observation time to track this interstellar visitor. JUICE launched in 2023 on its long journey to Jupiter's mysterious moons, happened to be positioned such that it could observe 3i Atlas from angles unavailable to Earth-based telescopes. The spacecraft's instruments captured images and spectra that complemented ground-based observations, creating a 3-dimensional understanding of the object's behavior. Ground-based facilities coordinated their efforts with the precision of a symphony orchestra. In Chile's Atacama Desert, where some of Earth's most powerful telescopes peer through exceptionally clear dry air, 3i Atlas became a regular target. The European Southern Observatory's Very Large Telescope allocated observation windows. Amateur astronomers with sophisticated equipment, modern citizen scientists, operating instruments that would have been considered professional grade just decades ago, contributed observations to international databases. In South Africa, telescopes tracked the object during Southern Hemisphere nights when northern observatories couldn't see it. In Australia, observers picked up the watch as the Earth's rotation carried the comet into their sky. This global coordination ensured nearly continuous monitoring, weather permitting creating an observational record with temporal resolution that would have been impossible for previous generations of astronomers. What did these observations reveal through summer and early autumn, an object following textbook orbital mechanics? Its position at any given moment matched predictions based on gravitational forces with remarkable precision. This is how celestial mechanics works. When thoroughly understood, you measure an object's position and velocity at several points, calculate the gravitational influences acting upon it from the sun and planets, and predict where it will be days, weeks, or months into the future. For 3i Atlas through September, predictions and observations aligned beautifully. Brightness measurements similarly tracked expectations. As the comet approached, the sun, solar heating increased. Frozen materials on its surface began sublimating, transforming directly from solid ice to gas without melting. This is the process that creates a comet's coma, the fuzzy cloud of gas and dust that surrounds the solid nucleus. As sublimation accelerated, the coma grew larger and brighter, following well-understood physical principles. Spectroscopic analysis provided glimpses of composition. When sunlight reflects off a comet and we analyze that light through a spectrograph, it gets broken into component wavelengths like a prism creating a rainbow. But unlike a smooth rainbow, cometary spectra show bright emission lines at specific wavelengths corresponding to specific molecules. The presence of hydroxyl molecules. OH radicals indicated water ice. Carbon emissions suggested organic compounds. These are standard cometary ingredients, the frozen remnants of our solar system's formation 4.5 billion years ago, preserved in the deep freeze of interstellar space. Comparisons with 2I Borisov were inevitable. That previous interstellar comet discovered in August 2019 had behaved so conventionally that it almost disappointed scientists hoping for exotic revelations. Borisov looked like, acted like, and compositionally resembled comets formed in our own solar system. It suggested that comet formation processes might be universal, that frozen volatiles Dust grains and rocky materials combine in similar ways, regardless of which star system hosts their creation. If Borisov represented the control case, proof that interstellar objects could be comfortingly familiar, then early observations of 3I Atlas suggested it might follow the same pattern. Through September, it gave every appearance of being another well-behaved visitor, interesting primarily because of its interstellar origin rather than because of unusual characteristics. But October approached, and with October came changes. In retrospect, an astronomy often operates in retrospect, recognizing patterns only after accumulating sufficient data. The first hints of anomalous behavior appeared around October 15th, approximately 2 weeks before perihelion. Brightness measurements began showing values slightly higher than predicted curves suggested. The discrepancy was subtle, within the realm of what could be attributed to natural variation in sublimation rates or uncertainties in the comet's size and albedo. Individual observatories noting this deviation might have questioned their calibration or attributed it to local atmospheric conditions affecting their measurements. But when multiple facilities documented the same trend independently, it became harder to dismiss. Then came velocity measurements showing something peculiar. Position tracking over multiple nights revealed that 3I Atlas wasn't quite where pure gravitational calculations predicted it should be. It was ahead of predictions, not dramatically but measurably. Something was accelerating it beyond the sun's gravitational pull. This phenomenon, non-gravitational acceleration, is actually well known in cometary science. As gas sublimes from a rotating comet's surface and streams into space, it creates a reactive force, like a natural rocket engine. Newton's third law: every action has an equal and opposite reaction. Gas escaping in one direction pushes the nucleus in the opposite direction. Astronomers routinely account for this effect in their orbital calculations. For well-studied comets that have passed through the inner solar system multiple times, non-gravitational acceleration parameters are refined with each passage, improving prediction accuracy. For a first-time visitor like 3I Atlas, some degree of non-gravitational acceleration was expected and wouldn't be concerning. What was concerning, or at least intriguing, was the magnitude. Based on the comet's estimated size and brightness, calculations suggested how much thrust sublimating gases should produce. The observed acceleration exceeded those estimates. Perhaps the size estimate was wrong. Perhaps 3I Atlas was smaller than calculated, meaning the same outgassing force would produce more acceleration. Perhaps it was more volatile-rich than typical comets, releasing more gas per unit of solar heating. These were reasonable explanations, and most astronomers adopted them as working hypotheses. But patterns were forming. Brightness higher than expected, acceleration greater than estimated, both anomalies in the same direction toward more activity, more energy release, more vigorous behavior than predictions suggested. Individually, each discrepancy could be explained through parameter adjustments. Together, they created a picture of an object that was almost following standard models, but not quite. Almost fitting expectations, but with subtle wrongness at the edges. As October progressed and perihelion approached, these subtle deviations persisted, and in some measurements intensified. The astronomical community's attention sharpened. Observation time at major facilities became more coveted. Amateur astronomers shared their images and data more frequently. Everyone wanted to see what would happen when 3I Atlas reached maximum solar heating. Everyone wanted to watch perihelion passage directly. But geometry wouldn't cooperate. As late October arrived, 3I Atlas's position in Earth's sky moved progressively closer to the sun's location. By October 28th, observing it required pointing telescopes uncomfortably near the solar disk, risking instrument damage from scattered light. By October 29th, at the moment of perihelion itself, the comet passed almost directly behind the sun from our perspective. For 3 days, direct optical observation became nearly impossible. The The most critical moment, maximum heating, maximum stress, maximum opportunity to observe dramatic changes, occurred behind a curtain of solar glare that our telescopes couldn't penetrate without risking permanent damage. We would have to wait and wonder what was happening in that invisible theater where fire met ice at 203 million kilometers from Earth. October 15th, 2025, 14 days before perihelion. At Lowell Observatory in Flagstaff, Arizona, astronomer Chi-Chang Jiang reviewed photometric measurements from the previous night's observations of 3I Atlas. The data showed the comet's brightness at magnitude 13.2 noticeably brighter than the predicted value of magnitude 13.7. Magnitude scales in astronomy run counterintuitively. Lower numbers mean brighter objects. A difference of 0.5 magnitudes represents roughly 58% more light reaching our instruments. This wasn't a subtle deviation. It was clear, measurable, and unexpected. Jiang's first action was standard procedure: verify the calibration. Check reference stars in the same field of view to ensure the instruments were measuring brightness accurately. Examine atmospheric conditions that might affect light transmission. Rule out mundane explanations before considering interesting ones. The calibration checked out. Reference stars showed expected values. Atmospheric conditions were typical for Flagstaff's excellent observing site. The anomalous brightness appeared to be real. Similar reports emerged from other observatories over the following days. In Chile, professional astronomers noted the same trend. In South Africa, independent measurements confirmed it. Amateur astronomers with carefully calibrated equipment documented identical behavior. This wasn't instrument error confined to a single facility. Multiple observers using different telescopes on different continents saw the same phenomenon. 3I Atlas was brightening faster than models predicted. To understand why this matters, consider how cometary brightness changes with solar distance. The relationship follows well-established physics. Solar heating intensity decreases with the square of distance from the Sun. If a comet doubles its distance from the Sun, it receives 1/4 the heating. Less heating means less sublimation, means smaller coma, means dimmer appearance. We can predict this relationship mathematically and test it against centuries of comet observations. It works, consistently, reliably. Comets brighten as they approach the Sun following curves we can calculate in advance with considerable accuracy. But 3I Atlas was brightening ahead of schedule. Its curve was steeper than physics suggested it should be. Something about this object, its composition, structure, or behavior, didn't match the models derived from thousands of previous cometary observations. 5 days later, on October 20th, a different kind of anomaly appeared in the data. NASA's Jet Propulsion Laboratory in Pasadena, California, maintains extraordinarily precise tracking of objects passing through our solar system. Their orbital mechanics team uses position measurements from multiple observatories to calculate trajectories accurate to within meters over millions of kilometers. For potentially hazardous asteroids that might someday threaten Earth, this precision could mean the difference between warning and catastrophe. For interstellar visitors, it allows detection of subtle forces acting on objects beyond simple gravitational attraction. On October 20th, JPL's analysis of Atlas's trajectory flagged an anomaly: non-gravitational acceleration. The comet was moving faster than gravity alone would predict. Not dramatically, the deviation was measured in meters per second of velocity change. But it was real, consistent across multiple observations, and statistically significant beyond measurement uncertainty. Non-gravitational acceleration isn't inherently mysterious. Comets experience it routinely through the rocket effect of sublimating gases. As frozen materials vaporize and stream away from the nucleus, conservation of momentum demands that the nucleus recoil in the opposite direction. Its thrust small but measurable, generated by natural outgassing. The question wasn't whether non-gravitational acceleration was occurring. The question was whether its magnitude matched expectations based on the comet's estimated properties. It didn't, not quite. Calculations suggested that a comet of 3I Atlas's estimated size and composition at its current distance from the Sun should be generating thrust from outgassing at a certain rate. The observed acceleration exceeded those estimates by roughly 20 to 30%. Not wildly excessive within the range that could potentially be explained by revising upward the comet's volatile content or revising downward its mass estimate, but enough to warrant flagging as anomalous pending further data. Here's what's crucial about pattern recognition in science. Individual anomalies can often be explained away. Measurement error, calibration drift, unusual but not impossible natural variation. The human mind is remarkably good at generating ad hoc explanations that preserve existing frameworks when confronted with data that don't quite fit. But when multiple anomalies appear simultaneously, when they cluster in time and seem related to each other, dismissal becomes harder. Forced explanations start feeling forced. 3I Atlas was now exhibiting two confirmed anomalies: unexpected brightness and excessive non-gravitational acceleration. Both appeared within the same 5-day window in mid-October. Both represented deviations from standard comet models in the direction of higher activity, more energy release, more vigorous behavior than the object's estimated properties should produce. Coincidence, parameter, estimation errors, or something genuinely unusual about this particular interstellar visitor. Professional astronomers remained cautiously non-committal in their public statements. More data were needed. The Perihelion passage would provide crucial observations. Patience was required before drawing conclusions. These are appropriate scientifically responsible positions when dealing with ambiguous data. But privately, in email exchanges between research teams and during conference calls coordinating observation campaigns, interest was intensifying. Whatever 3I Atlas was doing, it warranted closer scrutiny. Then came the color. Spectroscopic observations through late October revealed something unexpected about the light coming from 3I Atlas. The comet was reflecting and emitting light in wavelengths that gave it a distinctly blue coloration, not to the naked eye, which couldn't see it at all, given its faintness, but in the detailed spectral analysis that reveals an object's true colors beyond what human vision perceives. This was wrong, or at least highly unusual. Most comets approaching the Sun become redder. The physics is straightforward. Solar heating releases dust particles from the nucleus along with gases. These dust grains scatter incoming sunlight, and scattering affects shorter wavelengths. Blue light more strongly than longer wavelengths. Red light. It's the same physics that makes Earth's sky blue and sunsets red. For comets, increased dust activity means increased red coloration, giving them that characteristic rusty appearance in photographs. Blue coloration suggests the opposite: relatively little dust with light dominated by emission from ionized gases. Certain molecules, when excited by ultraviolet radiation from the Sun, emit light at specific wavelengths in the blue part of the spectrum. Carbon monoxide is one such molecule. When CO molecules absorb UV photons, their electrons jump to higher energy states, then cascade back down, emitting blue light in the process. So blue color isn't impossible or unprecedented for comets. Some gas-rich, dust-poor comets do show blue tinges. What was unusual was the timing and intensity. 3I Atlas was brightening rapidly, suggesting vigorous activity, but instead of the dusty reddish appearance such activity typically produces, it was becoming bluer. The spectral signature showed strong emission at wavelengths consistent with carbon monoxide. Almost consistent, very nearly consistent, but with subtle differences: some emission lines stronger than expected, others weaker, creating a pattern that was close to but not quite identical to the known spectroscopic fingerprint of CO. Perhaps it was CO with an unusual temperature or density distribution. Perhaps other molecules were contributing emission at nearby wavelengths, creating a blended spectrum that mimicked CO imperfectly. Perhaps the comet's composition included compounds rarely seen in solar system comets, reflecting its formation in a different stellar environment with different chemical abundances. These were all plausible explanations. None were definitive. By October 25th, 4 days before perihelion astronomers had documented 3 anomalies: brightness exceeding predictions by measurable amounts, non-gravitational acceleration stronger than estimated outgassing should produce, blue spectral coloration with emission lines that almost but don't quite match known molecules. Each anomaly had potential conventional explanations. Each could be accommodated within standard comet physics with appropriate parameter adjustments. But the accumulation was starting to feel less like coincidental measurement uncertainties and more like genuine, unusual behavior requiring explanation. And then came the visibility crisis. As October's final days arrived, 3I Atlas's position in Earth's sky moved progressively closer to the Sun's location. Angular separation, the apparent distance between two objects, as seen from Earth, decreased daily. By October 27th, the comet was positioned only 25 degrees from the Sun, roughly the width of 2.5 fists held at arm's length. Observing objects that close to the Sun requires extreme caution. Telescopes are designed to detect faint light from distant sources. Point 1. Accidentally at the Sun, even briefly, and the flood of solar photons can permanently destroy sensitive detectors designed to capture individual photons from faraway stars. It's like training a spotlight directly into your dark-adapted eyes. Instant blindness, sometimes permanent. Professional observatories can observe near the Sun by using careful timing, pointing just after sunset or just before sunrise when the Sun is below the horizon, but the target is still visible in twilight. Specialized solar telescopes use blocking filters and coronagraphs to observe the Sun's outer atmosphere while preventing the overwhelming light from the solar disk from reaching instruments. But these techniques have limits. On October 29th, at the moment of perihelion, 3I Atlas passed within about 10 degrees of the Sun as seen from Earth. For comparison, the Sun and Moon each appear about 0.5 degrees across. The comet was positioned 20 solar diameters from the Sun's edge in our sky, close enough that scattered sunlight made observation nearly impossible without specialized equipment. Worse, the geometry meant the comet was almost directly behind the Sun from our perspective. If you drew a line from Earth through the Sun, it would pass very near 3I Atlas's position. This configuration, called solar conjunction, represents the worst possible geometry for observation from our planet. For 3 days, from October 29th through October 31st, direct optical observation was largely impossible. The most critical phase of the comet's journey, when maximum solar heating produced maximum changes, occurred behind a curtain we couldn't penetrate. We lost surveillance exactly when surveillance mattered most, but we weren't completely blind. Space-based observatories operating in wavelengths other than visible light maintained partial observation capability. NASA's Neil Gehrels Swift Observatory, designed to detect gamma-ray bursts and operating in ultraviolet and X-ray wavelengths, turned its instruments toward 3I Atlas during perihelion passage. Ultraviolet light penetrates solar glare more effectively than visible light under certain conditions. Swift detected emission signatures from the comet throughout October 29th and 30th, particularly strong hydroxyl emissions, indicating water ice sublimating vigorously under solar heating. The intensity of these emissions exceeded what the comet's estimated size suggested it should produce, another data point suggesting either incorrect size estimates or unusual activity levels. ESA's JUICE spacecraft, positioned differently in its trajectory toward Jupiter, maintained visual observation capability through most of the perihelion window. JUICE captured images showing 3I Atlas's coma expanding and brightening, confirming that the comet was responding to solar heating, apparently surviving the thermal stress of closest approach. Radio telescopes on Earth, which operate in wavelengths unaffected by solar glare, tracked the comet's position throughout the invisible days, providing continuous trajectory measurements that would later reveal whether acceleration anomalies persisted during perihelion. So data continued accumulating. Not the high-resolution spectroscopy and detailed imaging astronomers wanted, but enough to confirm the comet's continued existence and document gross behavior patterns. On October 31st, as Earth's rotation and orbital motion carried us to positions where 3I Atlas emerged from behind the Sun's glare telescopes around the world, pointed toward the coordinates where it should reappear. Chi-Chang Jiang at Lowell Observatory captured the first post-perihelion optical image at 6:23 a.m. local time. The image showed a bright, diffuse coma surrounding the comet's nucleus, visible evidence of ongoing vigorous sublimation. And it showed something else. The comet was still distinctly blue. The acceleration anomaly persisted, now slightly decreased, as the comet moved away from peak solar heating, but still present at levels requiring explanation. And spectroscopic analysis over the following days confirmed that emission lines remained close to but not perfectly matching carbon monoxide patterns. Whatever had happened during those 3 invisible days behind the Sun, 3I Atlas had emerged changed. More active, more anomalous, more challenging to existing frameworks than it had been going in. The mystery had deepened, and the clock was ticking toward the December observation window that would determine whether answers emerged before the comet faded beyond detailed study. There's a particular frustration unique to astronomy watching a cosmic event approach with inexorable precision, calculating months in advance the exact moment when something scientifically crucial will occur, and then having geometry conspire to make that crucial moment unobservable. October 29, 2025, 11:47 Universal Time, Perihelion. At that precise moment, 3I Atlas reached its closest point to the Sun, 1.356 astronomical units, or approximately 203 million kilometers. At that distance, solar radiation struck the comet's surface at approximately 770 watts per square meter, enough energy to sublimate frozen materials vigorously to heat rocks, to potentially crack structures through differential thermal expansion. If the comet was a loosely bound aggregate of icy materials held together by weak forces, what astronomers call a rubble pile structure, like many comets appear to be, perihelion passage represented a severe stress test. Thermal shock, rapid outgassing creating internal pressure, rotational forces from spin, all conspiring to potentially tear the nucleus apart. Some comets don't survive perihelion. They fragment, break apart, disperse into clouds of debris that fade quickly as individual particles lack the mass to sustain a coma. Comet Ison, which garnered significant public attention in 2013, disintegrated during its extremely close perihelion passage, just 1.2 million kilometers from the Sun's surface. What went in as a promising bright comet came out as a dispersing debris cloud. Would 3I Atlas survive? Would it emerge intact fragments or somewhere between? We couldn't watch to find out. From Earth's perspective, the Sun's overwhelming brightness made direct observation impossible. Imagine trying to spot a firefly hovering next to a searchlight from a mile away. The searchlight's glare drowns out the firefly's faint glow completely. That's the observational challenge during solar conjunction. But our inability to watch doesn't mean nothing was happening. While Earth-based telescopes waited for the geometry to improve, 3I Atlas was experiencing the most intense heating of its entire journey through our solar system. Consider the physics. Solar radiation intensity follows an inverse square law. Double your distance from the Sun and you receive 1/4 the heating. At Earth's distance, 1 astronomical unit solar radiation delivers about 1,360 watts per square meter. At 3I Atlas's perihelion distance of 1.36 AU that drops to approximately 730 watts per square meter, though some calculations put it slightly higher depending on exactly how astronomical units are defined. For context, that's roughly the intensity of sunlight on a clear day at Earth's equator. Doesn't sound dramatic, perhaps. But remember, this object spent potentially millions of years in interstellar space at temperatures just a few degrees above absolute zero. Now suddenly, one side faces heating equivalent to tropical noon, while the other side remains in frigid shadow. The thermal shock is extreme. Frozen volatiles, water, ice. Carbon dioxide, ice, methane, ammonia begin sublimating, not melting. In the vacuum of space, these materials typically skip the liquid phase, entirely transforming directly from solid to gas. This process absorbs enormous energy, cooling the surface even as solar radiation heats it, creating complex temperature gradients. Gas escaping from the nucleus carries dust particles with it, creating the coma and tail we associate with comets. But gas release isn't uniform across the surface. Rotating comets develop active regions where concentrated jets of gas spray into space, creating asymmetric thrust that changes the nucleus's rotation rate and induces non-gravitational acceleration. All of this was happening to 3I Atlas during those 3 invisible days. The comet was reacting, changing, potentially fragmenting, definitely outgassing, all while we waited behind our planet's sunlit side for geometry to improve, enough that observation could resume. NASA's Swift Observatory did what it could. Operating in ultraviolet wavelengths, Swift detected strong hydroxyl emissions, OH molecules, the telltale signature of water ice sublimating. The presence of OH is actually how we detect water in space. H2O molecules get broken apart by ultraviolet radiation into hydrogen and hydroxyl, and the OH emissions show up clearly in UV spectra. The intensity Swift measured was striking. For an object of Atlas's estimated size, the amount of water sublimating calculated from OH emission strength exceeded typical rates by perhaps 50% or more. Either the comet was larger than estimated, meaning more surface area for sublimation, or it was sublimating unusually vigorously, or it had an unusually high water ice content compared to other comets. Each explanation has precedent. Comet size estimates derived from brightness measurements carry significant uncertainty. We're essentially trying to determine an object's diameter by measuring how much sunlight it reflects, which depends on both size and albedo surface reflectivity. Get the albedo wrong and you get the size wrong. Comets with surfaces often covered in dark, carbonaceous material have low albedos that make size estimation particularly challenging. Unusually vigorous sublimation could result from the comet's structure, perhaps, a highly porous, fluffy texture that allows solar heating to penetrate deeper than in more compact objects. Or perhaps the surface had a particularly thin layer of insulating dust, allowing heat to reach ice-rich subsurface materials more easily. High water content isn't impossible, though most comets show relatively consistent ratios between water ice and other volatiles, like CO and CO2. But most comets means comets formed in our solar system. 3I Atlas formed somewhere else under potentially different conditions. Maybe interstellar comets routinely have different compositions. We have a sample size of 3 interstellar visitors, hardly enough to establish statistical norms. ESA's JUICE spacecraft captured images during October 30th showing the comet's coma had expanded significantly. The fuzzy cloud of gas and dust surrounding the nucleus appeared larger and brighter than in pre-perihelion images, confirming vigorous outgassing. The coma showed some asymmetry, suggesting non-uniform activity across the nucleus surface, though detailed morphological analysis would have to wait for higher resolution post-conjunction observations. Radio telescopes on Earth maintained tracking throughout the invisible period. Radio waves with wavelengths measured in centimeters or meters, rather than the nanometers of visible light, aren't affected by solar glare the same way optical wavelengths are. Position measurements from radio observations allowed continued refinement of 3I Atlas's trajectory, and those measurements confirmed that non-gravitational acceleration persisted through perihelion. In fact, the acceleration appeared to intensify slightly during closest approach, exactly when solar heating peaked. This timing supports the outgassing explanation more. Heat drives, more sublimation produces more gas, creates more thrust. But the magnitude remained problematic. Even accounting for measurement uncertainties, the acceleration exceeded what models predicted based on estimated comet properties. These 3 days, October 29th, 30th, and 31st, represent a gap in our knowledge. Not complete blindness, but significantly reduced observational capability, precisely when the most dramatic changes were occurring. It's like watching a mystery film where the camera cuts away during the crucial reveal, then returns to show aftermath without letting you witness the event itself. Astronomers are methodical, patient people accustomed to working with incomplete data. They're comfortable extracting maximum information from limited observations and building understanding incrementally over time. But that patience exists in tension with the reality of opportunity windows. 3I Atlas offered one perihelion passage, one chance to observe maximum activity, one brief window when the object would be bright and active enough for detailed study. And that window occurred behind a solar curtain. When visibility returned on October 31st, when telescopes could finally observe the comet directly again, astronomers examined the first images with particular intensity. Had it fragmented? Was the nucleus still intact? Had activity levels changed? The answer that emerged over the following days was both reassuring and puzzling. 3I Atlas had survived perihelion intact. No obvious fragmentation into multiple distinct pieces. The nucleus appeared structurally sound, able to withstand the thermal and mechanical stresses of close solar passage. But it looked different. The coma was larger, brighter, more diffuse. The blue coloration was more pronounced. Spectroscopic measurements confirmed ongoing strong outgassing, and the trajectory data showed persisting non-gravitational acceleration, now gradually decreasing as the comet moved away from peak solar heating, but still present at levels requiring explanation. Something had changed during those invisible days. The comet that emerged from behind the sun wasn't quite the same object that had gone in, or at least our observations of it revealed characteristics that hadn't been as apparent before perihelion. Whether those changes represented natural evolution of comet activity under solar heating or something more unusual would become the central question for the December observation campaign. But first, astronomers needed to fully document what exactly the measurements were showing. What were the actual numbers? How did current observations compare to pre-perihelion data? What specific characteristics demanded explanation? That forensic analysis of the data would reveal the full scope of the anomalies. And it's to those measurements, to what the evidence actually shows, rather than what we hoped or expected it to show, that we now turn our attention. November 1st, 2025, 6:23 a.m. Mountain Standard Time, Lowell Observatory, Flagstaff, Arizona. Chichang Zhang reviewed the first post-perihelion optical image of 3I Atlas on his computer screen. The comet appeared as a diffuse glow against the star field, clearly brighter and more extended than in pre-conjunction observations. But what caught his attention immediately was something else: the color. Even in the raw, uncalibrated image, the comet showed a distinct blue tint. Not vibrant blue like a neon sign. Astronomical objects rarely appear as colorful to instruments as they do in processed publicity images, but unmistakably blue compared to the surrounding star's neutral white-yellow tones. Zhang initiated spectroscopic analysis protocols. Within hours, detailed wavelength measurements confirmed what the image suggested. 3I Atlas was emitting light dominated by wavelengths in the blue part of the spectrum, centered around 380–450 nanometers. This was wrong, or at least unexpected. Standard cometary behavior suggests the opposite trend. As sublimation intensifies, comets release increasing amounts of dust along with gases. Dust particles scatter incoming sunlight, and scattering affects short wavelengths. Blue more than long wavelengths. Red through Rayleigh, scattering the same physics that makes Earth's sky blue by scattering blue sunlight while allowing red to pass relatively unaffected. But for comets, where we're observing reflected sunlight rather than looking through an atmosphere, increased dust creates a reddish appearance. The more dust, the redder the color. Active comets approaching the sun typically turn increasingly red-brown as they shed material. Blue coloration suggests gas dominance over dust. Specifically, it indicates ionized molecules emitting light at specific wavelengths rather than dust-scattered continuum radiation. Certain molecules, when struck by ultraviolet photons from the sun, become electronically excited. Electrons jump to higher energy orbital states. When these electrons cascade back to lower energy states, they emit photons at specific wavelengths determined by the energy differences between quantum states. For carbon monoxide, one of the most common cometary volatiles, after water, those emission wavelengths fall in the blue part of the spectrum. CO molecules produce strong emissions around 400–450 nanometers when ionized by solar UV radiation. If a comet is rich in CO and relatively poor in dust, it can appear distinctly blue. But here's where 3I Atlas became puzzling. Detailed spectroscopic analysis showed emission lines consistent with ionized carbon monoxide, but not perfectly consistent. Some lines were stronger than expected, others were weaker. The overall pattern resembled CO, came very close to matching CO, but retained subtle differences that prevented unambiguous identification. Think of it like recognizing a familiar song played in a slightly wrong key, or a photograph of someone you know, but with features subtly off. Your brain recognizes the pattern as familiar, while simultaneously registering that something isn't quite right. Possible explanations emerged quickly. Perhaps the CO was at an unusual temperature or density, shifting the relative strengths of different emission lines. Temperature affects how molecules distribute among available energy states, which in turn affects emission line intensities. Perhaps other molecules were contributing emission at nearby wavelengths, creating a blended spectrum. Complex organic molecules can emit at wavelengths close to those of simpler compounds, making spectral interpretation ambiguous. Perhaps the comet contained carbon-bearing molecules rare or absent in solar system comets, compounds formed under different stellar conditions with different abundances of elements preserved through millions of years in interstellar space. Each explanation was plausible. None were definitive. The spectrum was close enough to CO that calling it CO felt reasonable, but different enough that nagging uncertainty persisted. Over the following days, as more observatories resumed tracking 3I Atlas with improving geometry, a fuller picture emerged. The coma had expanded significantly during perihelion passage. Pre-perihelion measurements estimated the coma at roughly 100,000 kilometers in diameter. Post-perihelion observations showed expansion to nearly 150,000 kilometers larger than Jupiter's diameter. This expansion confirmed vigorous outgassing during closest solar approach. But the coma's morphology showed interesting asymmetries. High-resolution images revealed subtle fan-shaped structures, extending from the nucleus, suggesting localized active regions where jets of gas were spraying preferentially in certain directions. This is common in comets. Rotating nuclei often develop enhanced activity on the sunward-facing hemisphere, creating directed jets. But the specific patterns in 3I Atlas's coma didn't match simple models of uniform rotation with a single active region. Multiple jets appeared to be operating simultaneously. Their orientations suggested complex rotation or perhaps multiple discrete active zones scattered across the nucleus surface. Determining which scenario was correct would require tracking coma morphology changes over time as the comet rotated. And there was the acceleration. NASA's JPL tracking, now incorporating October and early November positional measurements, confirmed non-gravitational acceleration persisting post-perihelion. The magnitude had decreased as expected when moving away from peak solar heating, but remained measurably above zero. The rate of decrease was slightly faster than standard outgassing models predicted, not dramatically so, but enough to constitute another small discrepancy between observation and prediction. It's worth pausing here to emphasize what non-gravitational acceleration means quantitatively. We're not talking about massive forces dramatically altering the comet's path. The acceleration detected was on the order of 10.6 to 10.7 meters per second squared millionths of a meter per second squared. For comparison, Earth's gravitational acceleration at its surface is about 9.8 meters per second squared. The non-gravitational acceleration acting on 3I Atlas was about 10 million times weaker. Over a day, this acceleration would change the comet's velocity by perhaps a centimeter per second. So why does it matter if it's so small? Because over the weeks and months of observation, these tiny accelerations accumulate. They shift the comet's position by kilometers compared to where pure gravitational calculations predict. And because we can measure positions to within meters, over millions of kilometers using modern astrometric techniques, detecting these shifts is possible. More importantly, the fact that acceleration is small doesn't mean it's insignificant scientifically. Any acceleration beyond gravity indicates forces acting on the object beyond simple orbital mechanics. Understanding what produces those forces, whether routine outgassing or something more unusual, is crucial for characterizing the object's nature. Through early November, as visibility continued improving with increasing angular separation from the Sun, spectroscopic campaigns ramped up. Multiple observatories allocated telescope time. Amateur astronomers with suitable equipment contributed observations. An international effort formed around characterizing 3I Atlas while it remained bright enough for detailed study. The European Southern Observatory's Very Large Telescope in Chile conducted high-resolution spectroscopy on November 5th. The data confirmed earlier observations, strong blue emissions, spectral signatures close to, but not perfectly matching carbon monoxide ongoing vigorous activity. Additional molecular species were detected: CN cyanogen, C2 diatomic carbon, both common in cometary coma. Their presence wasn't unusual. What was interesting was their relative abundances. The ratio of CN to C2 appeared higher than typical solar system comets show, though measurement uncertainties made this observation tentative rather than definitive. NASA's Swift Observatory continued UV observations, tracking hydroxyl emissions as a proxy for water production. Through the first week of November, OH emission remained strong, suggesting sustained sublimation of water ice. The production rate exceeded pre-perihelion levels as expected after solar heating, but the intensity remained higher than the comet's estimated size and distance would typically produce. By mid-November, the accumulated observations painted a clear, if puzzling, picture. 3IR Atlas had survived perihelion intact. Its nucleus showed no signs of major fragmentation. The outgassing creating its coma appeared vigorous, but not catastrophically so. It was behaving like an active comet, but the details didn't quite fit standard models. The blue color, the spectral anomalies, the excessive non-gravitational acceleration. The unusually strong water production individually explained through parameter adjustments, collectively forming a pattern of near explanations that never quite resolved into comfortable certainty. Mainstream media coverage at this point remained sparse. A few science journalism outlets reported that an interstellar comet had passed perihelion and remained active. Most articles focused on the basic facts. Third, confirmed interstellar visitor hyperbolic trajectory currently visible for dedicated observers. The anomalies went largely unmentioned in public-facing coverage. But within the astronomical community, interest was intensifying. Email exchanges between research groups discussed observation strategies for the approaching December window. Conference calls coordinated instrument time allocation. Preliminary findings were shared ahead of formal publication to ensure everyone had access to the emerging picture. ESA's JUICE spacecraft continued its dedicated observation campaign through late November. From its unique vantage point, JUICE captured images and spectra complementing Earth-based observations, building a three-dimensional understanding of the comet's activity patterns. Amateur astronomers increasingly equipped with sophisticated instruments and software contributed valuable data. Dozens of observers worldwide captured images night after night, documenting subtle changes in coma morphology and brightness. These observations uploaded to international databases provided temporal coverage that no single professional observatory could match. The comet was becoming a community research project. Professional astronomers, citizen scientists, automated sky survey spacecraft instruments, all focused on this small, faint object moving through its brief passage past our sun. And everyone was watching the calendar. December 19th, closest approach to Earth, the optimal observation moment. The final window for definitive characterization before 3I Atlas faded beyond detailed study. What would that window reveal? Would refined measurements resolve the anomalies into conventional explanations? Would they deepen the mystery by confirming characteristics that couldn't be accommodated within standard frameworks? The universe, as always, would answer in its own time. Our responsibility was to ask the right questions clearly enough that the answers, when they came, would be recognizable. Let me show you something fascinating about how science actually works when confronted with unusual observations. In November 2025, multiple research teams independently analyzed 3I Atlas observations accumulated from July through early November. They used different telescopes, different instruments, different analysis software, different methodological approaches. Yet they converged on essentially the same conclusions about what the data showed. This convergence, independent confirmation of the same findings, is how we distinguish real phenomena from instrumental artifacts or analysis errors. When one observatory reports something unusual, skepticism is appropriate. When 5 observatories using different equipment report the same thing, dismissal becomes difficult. Here's what the data actually show, stripped of interpretation or speculation, just measurements and their uncertainties. Brightness. Anomaly. Pre-perihelion predictions based on the comet's estimated size, albedo, and standard sublimation models suggested 3I Atlas would reach magnitude 11.5 at perihelion and magnitude 12.5 by mid-November. Actual measurements showed magnitude 10.8 at perihelion estimated from spacecraft observations during solar conjunction and magnitude 11.9 in mid-November. The comet was approximately 0.6 to 0.7 magnitudes, brighter than predictions, roughly 70–80% more light than expected. Multiple independent measurements confirmed this discrepancy. Lowell Observatory, European Southern Observatory facilities, amateur astronomers with carefully calibrated photometric systems all documented the same excess brightness within their measurement uncertainties. Why does this matter? Because brightness relates directly to coma size and activity level. A brighter comet indicates more material in the coma, scattering sunlight, which means more vigorous sublimation. The brightness excess suggests either that the comet is larger than estimated, meaning more surface area sublimating, or that it's sublimating unusually efficiently, meaning more gas released per unit area per unit time. Both explanations require revising our initial estimates about the comet's properties. The question is whether those revisions fall within typical parameter uncertainty ranges or require us to consider genuinely unusual characteristics. Non-gravitational acceleration. Orbital tracking through November showed persistent position deviations from pure gravitational predictions. The magnitude of non-gravitational acceleration varied with solar distance, as expected for outgassing-driven thrust, but remained measurably above what standard comet models predict, based on the object's estimated size and activity level. Quantitatively, the observed acceleration was approximately 1.5 to 2 times larger than models suggested it should be. This doesn't mean 1.5 times larger than expected for a comet. It means 1.5 times larger than expected for this specific comet with its estimated properties. The acceleration vector's direction varied over time, consistent with a rotating nucleus releasing gas, preferentially from active regions that change orientation as the comet spins. This behavior is normal for comets. What's unusual is the magnitude. Several possible explanations exist. The comet is smaller and less massive than estimated. Smaller mass means the same outgassing force produces more acceleration. Size estimates for faint, distant objects carry significant uncertainty. Perhaps a factor of 2 error wouldn't be shocking. The comet is more volatile-rich than typical. If it contains more frozen gases per unit, mass solar heating releases more material, creating more thrust. The comet's structure is unusually porous or fluffy. Lower bulk density means less mass to accelerate, so the same gas release produces more acceleration. Something else is contributing to acceleration beyond simple outgassing. The first 3 explanations are conventional. They work within standard comet physics by adjusting parameters. The fourth is where speculation begins, and where scientific conservatism demands extraordinary evidence before acceptance. Spectral anomalies. Resolution spectroscopy revealed emission lines at wavelengths consistent with ionized carbon monoxide, but with intensity ratios that don't perfectly match laboratory or astronomical standards for CO under typical cometary conditions. Specifically, certain rotational transitions within the CO electronic band system showed stronger emission than expected relative to other transitions. This could indicate unusual temperature, unusual density contamination from other molecular species, or potentially compounds we haven't fully characterized in cometary environments. Additionally, the Cn to C2 ratio appeared elevated compared to typical solar system comets, though measurement uncertainties make this conclusion tentative. If confirmed, it would suggest either unusual carbon chemistry or selective depletion of certain parent molecules that produce C2. Hydroxyl emissions detected by SWIFT showed production rates consistent with sublimating water ice at approximately 300-400 kilograms per second in early November. For comparison, typical active comets of similar estimated size at similar solar distances produce 100-200 kilos. 3I Atlas appears to be releasing water at roughly twice the expected rate. Either the comet is larger than estimated, meaning our brightness-based size calculation was wrong, or water ice is sublimating unusually efficiently, suggesting unusual surface properties, structure, or composition. Color measurements. Photometric observations in multiple wavelength bands confirmed blue coloration. Specifically, the comet appeared brighter in blue filters, B bands centered around 445 nanometers, relative to visible V bands centered around 551 nanometers, and red R band centered around 658 nanometers filters. The BV color index measured approximately plus 0.4, while typical dusty comets show values around plus 0.7 to plus 1.0. Lower values indicate bluer color. This confirms gas-dominated rather than dust-dominated emission, consistent with the spectroscopic detection of strong molecular emissions. However, the specific wavelength distribution doesn't match any single molecular species perfectly. It appears to be a blend of emissions from multiple compounds, making compositional determination ambiguous. Coma morphology. High-resolution imaging revealed multiple fan-shaped structures in the coma, suggesting several discrete active regions on the nucleus surface. The number, positions, and orientations of these features changed over time as the comet rotated, confirming they're tied to specific locations on the nucleus rather than being uniform across the surface. The rotation period estimated from coma feature changes appears to be approximately 16 to 18 hours. This is typical for comet-sized objects. Nothing unusual here. What is slightly unusual is the asymmetry of the activity distribution. Most comets show concentrated activity on the sunward hemisphere with perhaps one or two dominant jet sources. 3I Atlas appears to have 4 to 6 active regions distributed across the nucleus, though observational limitations make precise counting difficult. Trajectory. Evolution tracking data through November allowed refinement of the comet's hyperbolic orbit. The eccentricity is now calculated at approximately 6.1, with uncertainty confirming the object is definitively unbound from our solar system. Tracing the trajectory backward through space, accounting for gravitational influences from known stars and the galactic potential, suggests 3I Atlas has been traveling interstellar space for at least 10 to 50 million years. Its most recent close approach to another star system occurred millions of years ago, meaning it has been wandering the galactic medium for most humans' evolutionary history. Where did it come from? Originally, trajectory reconstruction points toward the general direction of Sagittarius, but tracing paths backward over millions of years accumulates massive uncertainties. We can say it came from that general region of the galaxy, but identifying a specific stellar system of origin is impossible. Now here's what's crucial about this data compilation. Every single measurement I've described has been confirmed by multiple independent observations. These aren't tentative preliminary findings from one research team. They're reproducible results documented by several groups using different instruments and analysis methods. The anomalies are real. They exist in the data independent of any single observer's expectations or biases. The question isn't whether 3I Atlas exhibits unusual characteristics, it demonstrably does. The question is what those characteristics actually mean. Do they represent extreme but natural variation within known comet physics? Do they require expanding our models to accommodate processes we haven't adequately considered? Or do they point towards something genuinely unprecedented that doesn't fit existing frameworks? That question the interpretation of confirmed observations is where scientific debate properly occurs, and it's to those competing interpretations, those alternative frameworks for understanding what we're seeing, that we now must turn our attention. Let me walk you through how most astronomers are thinking about 3I Atlas, because the conventional explanation deserves our careful attention before we consider alternatives. The standard model holds that 3I Atlas is a natural comet composed of frozen volatiles, water ice, carbon dioxide, carbon monoxide, methane, ammonia, mixed with dust grains and rocky material. This composition is unremarkable. It's what we expect for objects formed in the cold outer regions of planetary systems, where temperatures allow these materials to freeze solid. Under this model, every observed anomaly can be explained through parameter adjustments within the range of natural variation we see in cometary populations. Explaining excess brightness. The brightness anomaly disappears if we revise the comet's size estimate upward. Instead of 1-2 kilometers in diameter, perhaps it's 3-4 kilometers. Or instead of an albedo surface reflectivity of 0.04 typical for dark carbonaceous comet surfaces, perhaps it's 0.06 or 0.08. These revisions aren't radical. Size and albedo estimates for distant faint objects carry substantial uncertainty. Brightness measurements tell us the total amount of light reflected, but disentangling size from reflectivity requires additional information we often don't have. We make educated guesses based on typical values for similar objects, but typical admits wide variation. If 3I Atlas is simply larger than initially estimated, its greater surface area naturally produces more sublimation, more coma material, more brightness. Problem solved through straightforward parameter revision. Explaining non-gravitational acceleration. The acceleration anomaly disappears if the comet is smaller and less massive than estimated. Smaller mass means the same outgassing force produces more acceleration. Newton's second law force equals mass times acceleration. Rearrange to get acceleration equals force divided by mass. Reduce mass, increase acceleration. Alternatively, if the comet is more volatile-rich than typical solar heating, releases more gas per unit area, generating more thrust. Or if its structure is highly porous, more like aerogel than solid ice bulk. Density decreases, reducing mass without changing size estimates. These scenarios work within standard physics. They require no new processes or exotic materials. They simply place 3I Atlas at one end of the natural variation spectrum. Explaining spectral anomalies. The blue color and near CO emission pattern resolve if the comet has an unusually high gas-to-dust ratio. Some comets are dusty, releasing substantial particulate matter that reddens their appearance. Others are gassy, releasing mostly volatile molecules with minimal dust contamination. If 3I Atlas formed in a region of its birth system where dust was depleted or volatile ices were enhanced, it could naturally be gas-dominated. The specific spectral signature close to but not perfectly matching pure CO results from a mixture of molecules, CO plus CnC2CH, and other carbon-bearing species that blend to create the observed pattern. Temperature and density gradients within the coma can shift emission line intensities, explaining why the spectrum doesn't match laboratory standards perfectly. Real astronomical objects are messier than controlled laboratory conditions, and minor discrepancies in spectral details are routine. The historical precedent. This conservative approach has strong historical support. Many comets initially appeared anomalous before refined observations revealed they fit standard models after all. Comet Hale-Bopp in the 1990s showed surprisingly high activity levels far from the Sun, initially puzzling astronomers. Eventually, analysis revealed it was simply enormous. 40 kilometers in diameter and rich in carbon monoxide, which sublimates at greater solar distances than water ice. Understanding its size and composition explained the anomalous behavior. Comet Hartley 2 exhibited unusual non-gravitational acceleration that seemed excessive for its size. Spacecraft flyby missions revealed it was shaped like a peanut rotating end over end, with concentrated jets spraying from specific locations. The shape and rotation pattern explained the acceleration anomalies. History suggests that apparent anomalies often disappear with better data and more sophisticated analysis. What seems mysterious at first reveals itself as natural variation once we understand the specific circumstances properly. Why this remains the leading hypothesis. Scientific conservatism. The principle that extraordinary claims require extraordinary evidence weighs heavily in favor of conventional explanations. We don't invoke new physics or unprecedented phenomena unless absolutely necessary. If existing frameworks can accommodate observations through parameter adjustments, that's where we should start. The standard comet model has centuries of refinement behind it. It successfully explains thousands of observed comets. It's grounded in well-understood physics of sublimation gas dynamics, orbital mechanics. Abandoning it requires overwhelming evidence that no combination of parameter adjustments can fit the data. Do we have that evidence for 3I Atlas? Most astronomers would say no, not yet. The observations are unusual, but unusual isn't impossible within natural variation, the discomfort. But, and this is important, accepting the standard model for 3I Atlas requires adjusting multiple parameters simultaneously, all in the same direction, all toward values at the edge of typical ranges. We need the comet to be larger than initially thought to explain brightness, but smaller than initially thought to explain acceleration. Unless we also invoke much higher porosity and lower bulk density, which is possible but requires yet another parameter adjustment. We need unusually high volatile content to explain vigorous activity, but unusually low dust content to explain blue color. Again, possible some comets are indeed gas-rich and dust-poor, but it's another specific requirement. We need the spectral signature to result from blended molecular emissions in just the right proportions to mimic carbon monoxide imperfectly. Possible but specific. Each individual adjustment is plausible. Taken together, they describe an object that's unusual in multiple correlated ways. Not impossible, not unprecedented, but definitely at the boundary of typical behavior. Think of it like this. Imagine someone who is 99th percentile in height, 99th percentile in arm length, 99th percentile in hand size, all simultaneously. Each trait individually is within human variation, but finding them all in one person becomes progressively less likely as you add more extreme traits. 3I Atlas appears to be a 99th percentile comet in several characteristics simultaneously. Unusual, but perhaps not impossibly so, given that interstellar comets formed in different environments might naturally differ from solar system comets formed in our specific conditions. The standard model says, all of this is explainable within known physics and natural variation. We just need to recognize that this particular comet sits at one tail of the distribution in multiple characteristics. Is that the right explanation? Probably. Most astronomers working on 3I Atlas would say yes, this is most likely what we're seeing. But the accumulation of parameter adjustments required the need for multiple simultaneous extremes creates intellectual discomfort. Not proof of anything exotic, just discomfort. A nagging sense that the puzzle pieces are being forced to fit rather than clicking naturally into place. And when discomfort persists despite best efforts to apply conventional frameworks, science demands we at least consider whether alternative explanations might exist, not as preferred hypotheses but as possibilities deserving evaluation. Which brings us to the next set of interpretations, the unusual but still natural explanations that expand standard models without abandoning them entirely. Sometimes the simplest explanation for unusual behavior is structural failure. Comets aren't solid objects like rocks or metal. They're fragile aggregates of ice and dust weakly bound by self-gravity that's barely sufficient to hold material together. The nucleus is more like a dirty snowbank than a boulder, porous, fragmented internally, with structural strength provided primarily by frozen ices, acting as cementing agents. Put such an object through the thermal stress of perihelion passage, and breakup becomes possible. The fragmentation scenario. Picture 3I Atlas as it approaches the sun. One hemisphere faces continuous solar heating, while the other remains in frigid shadow. Temperature gradients develop perhaps several hundred degrees difference between the sunlit and shadowed sides. Materials expand when heated, contract when cooled. Different materials expand and contract at different rates. Structural stress builds. Simultaneously, subsurface ices begin sublimating. Gases form beneath the surface and build pressure-seeking escape routes. Cracks propagate. Weak points fail. What started as a single solid nucleus begins developing fissures. Fractures may be complete separations. On October 29th, during closest approach, when thermal stress peaked, perhaps 3I Atlas fragmented. Not catastrophically, not completely dispersing into debris, but significantly. The nucleus split into several large pieces or shed substantial surface material or developed major structural cracks that increased the area of exposed ice. This scenario explains several anomalies simultaneously: fragmentation and brightness. Freshly exposed interior material suddenly subject to direct solar heating for the first time would sublimate vigorously. The exposed ice hasn't been processed by prior solar radiation, hasn't developed an insulating dust layer, hasn't been depleted of volatiles. It's pristine, highly reactive, ready to release gases in abundance. This surge of sublimation dramatically increases coma brightness, not because the comet was originally larger than estimated, but because breakup suddenly increased the effective surface area exposed to space. Historical precedent supports this comet Shoemaker-Levy 9, which famously collided with Jupiter in 1994, had previously fragmented into more than 20 pieces during a close pass by Jupiter in 1992. Each fragment developed its own coma, and the total brightness of the fragment ensemble exceeded what the original single nucleus had displayed. Fragmentation and acceleration. Fragmentation releases material suddenly and asymmetrically. Large chunks separating from the main nucleus carry momentum. The recoil from that separation creates thrust additional non-gravitational acceleration beyond what routine outgassing would produce. Additionally, freshly exposed surfaces on fragments outgas vigorously, creating reactive thrust from multiple locations simultaneously rather than from a single rotating nucleus. The vector sum of these multiple thrust sources could plausibly exceed typical outgassing acceleration. Fragmentation and spectral anomalies. Interior materials might have different composition than surface materials. If the comet's outer layers were depleted in certain volatiles through prior processing, while interior regions retained original pristine composition, breakup would suddenly expose material with different chemistry. The spectral signature not matching standard CO perfectly could result from this compositional inhomogeneity, a mix of processed surface material and unprocessed interior, creating blended emission that resembles but doesn't identically match pure molecular species. What would confirm fragmentation? December observations hold the key. If 3I Atlas fragmented during perihelion, several signatures should be detectable. Multiple discrete condensations in the coma, bright spots indicating separated fragments, each with its own sublimation envelope. Asymmetric coma, morphology inconsistent with single rotating nucleus complex patterns, indicating material distribution from breakup. Changing brightness as fragments evolve differently. Some remaining, active, others fading. As volatiles deplete, spectral evolution as different fragments display different composition. High-resolution imaging in December could reveal these features if they exist. Conversely, if December observations show a single compact nucleus with symmetric coma, typical of intact comets, fragmentation becomes less plausible. The internal heat scenario. Alternatively, consider a different, unusual but natural explanation: internal heat generation. Most comets are cold objects. Their interiors remain frozen solid, warmed only slowly by solar radiation penetrating inward through thermally insulating surface layers. Activity is driven almost entirely by external solar heating of surface and near-surface materials. But what if 3I Atlas contains significant concentrations of radioactive isotopes? Radioactive decay generates heat. In planetary contexts, this internal heat drives geological activity. Earth's molten core and active tectonics are powered partly by radioactive decay of uranium, thorium, and potassium in our planet's interior. The Moon was geologically active early in its history, powered by internal heat. Could a comet harbor enough radioactive material to generate significant internal heat? It's unusual but not impossible. Comets form from the solar nebula, the rotating disk of gas and dust that collapse to create our sun and planetary system. That nebula contained trace amounts of radioactive elements incorporated into all solid materials. Typical concentrations are far too low to generate meaningful heat in comet-sized objects. But if 3I Atlas formed in an unusual region of its birth nebula, or if it incorporated materials from a nearby supernova explosion that enriched local space with freshly synthesized heavy elements, radioactive concentrations could be elevated. Internal heat and anomalies. An internal heat source would drive sublimation more vigorously than solar heating alone. The comet would release more gas than its solar distance suggests it should, explaining excess brightness and activity. Non-gravitational acceleration would exceed typical values because more gas means more thrust. The acceleration might not decrease with solar distance as quickly as expected because internal heat doesn't diminish the way solar heating does when moving away from the sun. The blue color could result from specific chemistry, perhaps. CO ice sublimating preferentially from internal regions where heat drives selective volatile release before other compounds. What would confirm? Internal heat infrared observations in December could detect thermal emission indicating temperatures higher than solar equilibrium. If the comet is radiating more infrared light than it receives from the sun, internal heat becomes plausible. Additionally, if activity levels remain higher than expected for the comet's increasing solar distance through December and January, internal heat provides an explanation. However, generating sufficient heat from radioactive decay to detectably affect a kilometer-sized comet requires quite unusual abundances. It's speculative, though not impossible. The combined scenario, perhaps both fragmentation and internal heat played roles. An internally heated comet experiencing thermal stress might fragment more easily than a purely cold object. Breakup would then expose internally heated materials to space, creating the observed vigorous activity. This combined explanation accommodates multiple anomalies through two interconnected natural processes neither individually unprecedented, but their coincidence in one object uncommon. Why these hypotheses matter: fragmentation and internal heat represent expansions of standard comet models rather than rejections. They work within known physics structural failure, and radioactive decay are thoroughly understood processes. They simply apply those processes in combinations we don't routinely observe. If either proves correct, 3I Atlas teaches us about the diversity of comet behaviors and the range of conditions under which comets can form and evolve. But it doesn't require revolutionary new physics or exotic explanations. Science advances by expanding categories when observations demand it. If comets can occasionally fragment during perihelion or contain unusual radioactive concentrations, our models become more sophisticated without becoming radically different. The December observation window will test these hypotheses directly. Fragmentation leaves observable signatures. Internal heat produces detectable thermal anomalies. Either should be confirmable or refutable with appropriate measurements. And if both fragmentation and internal heat are ruled out, if 3I Atlas remains intact with no evidence of thermal excess, then we're left with the third set of explanations. The speculative ones, the uncomfortable possibilities that push against the boundaries of what we consider natural. This is where intellectual honesty requires acknowledging that science sometimes encounters phenomena that don't fit neatly into existing frameworks, where conventional explanations feel forced, where alternative interpretations, however speculative, deserve consideration, not acceptance, not endorsement, but consideration openly and without prejudice as we examine what the evidence actually shows. Before we proceed, let me be absolutely clear. What follows is speculation requiring extraordinary evidence we don't yet possess. These ideas exist at the boundary of known science, some firmly within physics, some venturing into territory where certainty dissolves into possibility. This is the smallest portion of our analysis for good reason. Extraordinary claims require extraordinary evidence. The evidence for a three-eye atlas is unusual, but unusual isn't extraordinary. It's data that challenges standard models without definitively refuting them. But intellectual honesty demands we acknowledge when conventional frameworks require increasingly forced adjustments to accommodate observations. And when that happens, science benefits from considering not embracing, but considering whether alternatives might exist that better fit the evidence. The artificial origin question. Harvard astrophysicist Avi Loeb has spent considerable professional capital arguing that we should seriously consider technological explanations for certain anomalous interstellar objects, particularly Oumuamua and now Three-Eye Atlas. His argument isn't that these objects are definitely artificial. It's that their characteristics cluster in ways that would be consistent with technology while being unusual for natural objects, and that dismissing technological possibilities without investigation betrays scientific objectivity. For Three-Eye Atlas, Loeb points to several factors. The blue coloration that doesn't quite match known natural molecular emissions. If ionized gases from some propulsion exhaust were mixed with natural comet outgassing, you might get exactly this kind of close but not perfect spectral match. The non-gravitational acceleration exceeding natural outgassing predictions. If thrust were coming partly from directed propulsion rather than passive gas release, the magnitude and vector evolution might differ from typical cometry behavior. The timing arriving at inner solar system becoming most active during perihelion emerging changed could be consistent with a trajectory designed to use solar heating or solar proximity for some purpose. The trajectory itself which brings it near Mars, Venus, and Jupiter, but not Earth, as if avoiding too close approach to our planet. Now, before anyone jumps to conclusions, none of this proves anything. Each observation has conventional explanations we've already discussed. The spectral signature is almost CO, probably is CO with measurement uncertainties. The acceleration is explainable through parameter adjustments. The timing is what orbital mechanics dictates for any object on this trajectory. But Loeb's fundamental point is epistemological. How do we distinguish natural from artificial at cosmic scales? What would a technological object disguised as or actually composed of comet material look like? Would we even recognize it? If an advanced civilization wanted to explore stellar systems using small probes camouflaged within comet-like shells makes strategic sense. Solar heating would provide power. Outgassing would provide propulsion. The object would appear natural to casual observation while potentially being directed. This isn't science fiction speculation, it's an honest question about observational signatures. If technology exists at interstellar scales, how would we detect it? What evidence would be definitive? The uncomfortable answer is, we don't really know. We've never detected extraterrestrial technology. We don't have verified examples to compare against. We're making educated guesses based on what we think technology might look like scaled up to cosmic engineering. The burden of proof. This hypothesis faces enormous evidential burden. Extraordinary claims require extraordinary evidence, and current observations are unusual but not extraordinary. Definitive evidence for artificial origin would include directed acceleration inconsistent with outgassing geometry, thrust in directions that can't be explained by reactive forces from sublimating gases, radio transmissions at frequencies and with modulation patterns inconsistent with natural emission, regular geometric structure visible in high-resolution imaging shapes that natural processes don't produce, compositional anomalies indicating refined materials rather than primitive ices and rocks, trajectory changes that violate conservation of momentum, absent reactive thrust from mass ejection. None of these have been detected for Three-Eye Atlas. The acceleration is consistent with asymmetric outgassing. No confirmed radio signals have been detected despite online claims that have no peer-reviewed backing. No geometric structure appears in images. The coma is diffuse and morphologically comet-like. Composition appears consistent with icy volatiles. Trajectory follows gravitational and outgassing physics. So why mention the artificial hypothesis at all if evidence doesn't support it? Because science proceeds by eliminating possibilities. We can only confidently assert something is natural if we've seriously considered and ruled out alternatives. Dismissing technological explanations without investigation, simply assuming they're impossible or refusing to think about them, creates blind spots that could cause us to miss genuine discoveries. Avi Loeb's advocacy for considering technological possibilities has made him controversial. Many colleagues view his public statements as premature, given insufficient evidence. They worry about legitimizing fringe speculation or encouraging conspiracy theories. But his core methodological point is valid, extraordinary conservatism, refusing to even consider possibilities outside conventional frameworks is as unscientific as extraordinary credulity. The proper scientific stance is neither "it's definitely natural" nor "it might be artificial ma," but rather, here's what evidence would distinguish these hypotheses, and here's what we actually observe. Unknown. Natural processes. A less radical but still speculative possibility is that 3I Atlas is entirely natural, but behaving through processes we haven't adequately understood or observed in solar system comets. Interstellar space differs dramatically from the environment within stellar systems. Radiation fields are weaker. Temperatures hover just above absolute zero. Cosmic rays bombard materials for millions of years. Chemical evolution proceeds differently than in warmer, denser nebular environments. Perhaps ice structures formed under these conditions have properties we haven't characterized. Perhaps organic compounds synthesize through radiation chemistry that doesn't occur in our solar nebula. Perhaps magnetic fields frozen into materials during formation affect sublimation patterns in ways we don't model. These aren't exotic physics, they're normal physics applied to conditions we don't have direct experience with. We've never studied materials that spent millions of years in true interstellar conditions. The 3 interstellar visitors we've detected are our only samples. If 3I Atlas is teaching us that interstellar comet chemistry differs systematically from solar system comet chemistry, that's scientifically valuable even if not revolutionary. It expands our understanding of comet diversity without requiring us to abandon natural explanations. The intellectual honesty argument. Here's what responsible speculation looks like. We have observations that don't perfectly fit standard models. We've identified several conventional explanations that might work with parameter adjustments. We've considered unusual but natural processes like fragmentation or internal heat, and we've acknowledged that more exotic possibilities exist, however unlikely, that can't be completely ruled out with current data. The proper conclusion is, we don't know yet. More observations are needed. December measurements will help distinguish between competing hypotheses. Until then, maintaining openness to multiple explanations, weighted by their prior probability and evidential support, is intellectually honest. This isn't claiming 3I Atlas is artificial or unprecedented. It's acknowledging that the data don't yet definitively constrain interpretation to a single explanation, and that science benefits from considering the full range of possibilities explicitly rather than assuming one framework must be correct. What December might reveal. If 3I Atlas is artificial, which remains highly speculative, December observations might detect trajectory modifications inconsistent with outgassing physics, geometric structures in high-resolution imaging, compositional anomalies in detailed spectroscopy radio emissions with non-natural characteristics. If it's natural but involves unknown processes, December might show chemistry inconsistent with solar system formation conditions, ice structures, or sublimation patterns not seen in solar system comets. activity levels that can't be reconciled with standard models, even with parameter freedom. If it's simply an unusual but conventional comet, December should show characteristics that fit within standard models. Once better constrained, no signatures requiring exotic explanations, resolution of anomalies through refined measurements. The universe will answer. Our responsibility is to ask clearly and listen carefully to what the evidence actually says. Here's a paradox that deserves examination. We can photograph galaxies 13 billion light-years away, resolve individual stars in neighboring galaxies, detect exoplanets orbiting distant suns by measuring the dimming of starlight when they pass in front of their host stars. Yet 3I Atlas, a mere 150 million miles away in mid-November, remains frustratingly difficult to observe with the detail these anomalies demand. Why? The technical answer reveals something profound about the limitations of even our most sophisticated instruments, and about the particular challenges of studying small, faint, fast-moving objects in our cosmic neighborhood, the problem of size and brightness. 3I Atlas is small. Current estimates place its nucleus somewhere between 1 and 5 kilometers in diameter, roughly the size of a mountain, but tiny on cosmic scales. At 150 million miles, this translates to an angular size far too small to resolve as anything but a point source, even with our largest telescopes. The Hubble Space Telescope, with resolution around 0.05 arcseconds under ideal conditions, could theoretically resolve features about 360 kilometers across at 3I Atlas's distance. The nucleus itself subtends about 0.001 arcseconds, 20 times smaller than Hubble's resolution limit. We can't see its shape, can't distinguish surface features, can't directly image its structure. What we observe is the coma, the cloud of gas and dust surrounding the nucleus. This extended envelope is large enough to study, but diffuse, constantly changing with brightness gradients that make precise measurement challenging. Reading composition from coma emissions tells us what's being released, but not necessarily what the nucleus contains. Some materials sublimate readily, others remain locked in ice until much higher temperatures are reached. And the brightness itself poses challenges. At magnitude 1213 in mid-November, 3I Atlas is roughly 250 times fainter than the faintest stars visible to the naked eye under perfect dark sky conditions. Observing it requires substantial telescopes, apertures of at least 20-30 centimeters. To detect it visually, larger instruments for detailed spectroscopy or photometry. The challenge of motion. At 42 miles per second during perihelion, 3I Atlas was moving fast enough to cross the width of the full moon in about 10 seconds as seen from Earth. This creates motion blur in long exposure photographs, the standard technique for capturing faint objects. Astrophotography typically involves exposing for minutes or even hours, allowing photons to accumulate on detectors until faint objects become visible. But exposure durations are limited by how much an object moves during that time. Too long, and instead of a sharp point or well-defined coma, you get a streak. Tracking mounts can compensate by following the object's predicted motion, but prediction accuracy decreases for newly discovered objects whose orbits haven't been fully constrained. Small tracking errors accumulated over long exposures degrade image quality. The speed also means observation windows are brief. By the time you've completed one night's observations, calculated what you want to observe. Next night, coordinated telescope scheduling, the object has moved. Its solar distance has changed, affecting activity levels. Its orientation may have changed through rotation, presenting different active regions. You're always chasing a target that won't hold still, the solar glare problem. We've discussed the October visibility crisis, but it's worth understanding why solar proximity creates such severe observational problems. Telescopes detect light by collecting photons and focusing them onto detectors. Those detectors are exquisitely sensitive. Modern CCD and CMOS sensors can register individual photons arriving from distant astronomical sources. This sensitivity is essential for studying faint objects, but it makes them vulnerable to bright sources. Point a telescope toward the sun, even briefly, and the flood of solar photons overwhelms the detector, potentially causing permanent damage. It's like looking at a welding arc with dark-adapted eyes, instant harm through overstimulation. Solar observatories use specialized filters that block 99.9999% of incoming light, allowing just enough through to study solar features without destroying instruments. But these filters make everything else invisible. You can observe the sun or observe everything else, but not both simultaneously. When 3i Atlas passed near the sun in our sky, the angular separation dropped below safe limits for direct observation. Pointing instruments toward the comet meant pointing dangerously close to the solar disk. Scattered sunlight light bouncing off dust in Earth's atmosphere, off telescope optics, off any surface between sun and detector, overwhelmed the faint signal from the comet. The sun is 400,000 times brighter than the full moon, which itself is 400,000 times brighter than the faintest stars visible to naked eye. That's 160 billion times brighter than faint stars. Detecting a magnitude 12 comet positioned 10 degrees from the sun is like trying to spot a firefly next to a stadium spotlight. Space-based observatories partially overcome this by operating above Earth's atmosphere, eliminating one source of scattered light. But they still face limits. Solar panels must be oriented toward the sun for power. Heat shields protect sensitive instruments from solar radiation. Pointing constraints prevent instruments from looking too close to the sun, protecting them from thermal damage and overwhelming light. What we can and cannot determine. Given these limitations, what can we actually measure about 3i Atlas position extremely accurately? Astrometric measurements can determine the comet's location in the sky to within fractions of an arc-second, translating to position accuracy of roughly 100 kilometers at its current distance. This allows precise trajectory calculations and detection of non-gravitational acceleration. Brightness. Accurately, with careful calibration, photometric measurements in different wavelength bands reveal total light output and color, though absolute brightness. Calibration requires comparing to standard reference stars and accounting for atmospheric extinction and instrumental response. Composition partially. Spectroscopy reveals which molecules are present in the coma through their emission and absorption lines, but spectral resolution limits how precisely we can identify species. Low-resolution spectra might show broad features consistent with several different molecules. High-resolution spectroscopy requiring larger telescopes and longer exposures provides better discrimination, but is more challenging for faint moving targets. Activity patterns. Qualitatively, we can see that the coma is asymmetric, that features appear and disappear over time, that brightness varies. But translating these observations into detailed models of nucleus rotation, active region distribution, and outgassing physics requires assumptions about structure and composition. We can't directly verify. Mass poorly. Direct mass measurement requires observing gravitational influence on other objects. But 3i Atlas isn't passing close enough to anything massive enough to measurably perturb. We estimate mass from brightness using assumptions about size and density, but those assumptions carry enormous uncertainty, potentially factors of 2, 3, or more. Internal structure. Not at all currently. Determining whether the nucleus is solid, porous, fractured, or rubble pile requires either direct imaging, impossible at this distance, radar observation. The comet is too far for useful radar returns, or spacecraft flyby not available for this target. We infer structure from indirect evidence like rotation rates and how the object responds to stress, but verification is impossible. The information gap. These limitations create an information gap, not a conspiracy or cover-up, but genuine technical constraints that prevent the comprehensive, continuous, high-resolution monitoring that would definitively answer many questions. We have snapshots, observations from different instruments at different times, capturing different aspects of the comet's behavior. We have enough data to document anomalies to recognize that something unusual is occurring, but not enough to definitively explain those anomalies beyond reasonable doubt. Think of it as trying to understand an elephant when you can only touch it briefly in darkness from 100 meters away. You can determine approximate size that it's moving, that it seems to have unusual features. But definitive identification requires closer, clearer, more extended observation than circumstances permit. This is the reality of astronomical observation. We work with available light across vast distances with instruments that represent humanity's best efforts but remain fundamentally limited by physics and engineering. The universe doesn't optimize itself for our convenience, and the most interesting phenomena often occur precisely when observation is most challenging. Why other observatories succeeded, where some struggled. Lowell Observatory captured the first post-perihelion image, not because they have uniquely superior equipment. Many facilities operate larger telescopes, but because they had the right combination of location timing and observer expertise. Flagstaff, Arizona sits at 7,000 feet elevation in a region with typically clear skies and low light pollution. When visibility improved on October 31st, Lowell had clear weather, while some other observatories faced clouds or poor atmospheric conditions. Timing mattered. Qichang Zhang's expertise with faint-moving objects from years of near-Earth asteroid work meant he knew how to optimize exposures for maximum signal while minimizing motion blur. Experience matters. Amateur astronomers worldwide, now equipped with instruments that would have been professional-grade decades ago, contributed observations that filled gaps when major observatories were clouded out or allocated to other targets. Their ability to observe targets of opportunity without formal scheduling months in advance provided valuable coverage. ESA's JUICE spacecraft observed from a fundamentally different position in space, creating parallax that provided three-dimensional information unavailable to Earth-based observers. Geometry matters. The international coordination professionals, amateurs, spacecraft observatories across continents created a distributed network that maximized coverage despite individual limitations. No single observer saw everything, but collectively, the community captured a comprehensive record. This is modern astronomy at its best, collaborative multi-platform leveraging diverse capabilities to overcome individual constraints. It's also astronomy revealing its limits. Despite best efforts, critical observations during perihelion passage remained impossible. The 3-day gap persists in the data. What happened behind the sun, we can only infer, never directly witness. Time in astronomy is peculiar. Most phenomena operate on scales incomprehensible to human experience. Stars evolving over billions of years, galaxies colliding across hundreds of millions of years, the universe itself expanding for nearly 14 billion years since the Big Bang. But occasionally, cosmically brief windows open when specific observations become possible, then close forever. 3i Atlas offers such a window measured in weeks, rapidly narrowing toward inaccessibility. December 19, 2025 marks closest approach to Earth. 1.80 astronomical units, approximately 167 million miles. This is the optimal geometry. Minimum distance means maximum brightness, maximum angular size of the coma, minimum motion across the sky per unit time. Best opportunity for high-resolution observations before the comet fades beyond detailed study. The timeline: current status early November. Visible magnitude 11.9, 12.2 depending on activity fluctuations. Observable with amateur telescopes from dark sites. Professional facilities conducting regular photometry and spectroscopy. ESA's JUICE spacecraft maintaining observation campaign through November 25th, mid-November. Through early December, brightness slowly declining as solar distance increases but still accessible to most professional instruments and dedicated amateur observers. Angular separation from Sun continuing to increase, improving observation geometry. Weather becomes the primary constraint. Northern Hemisphere winter brings increased cloud coverage to many observatory sites. December 10, 25, optimal observation window. Closest approach on December 19th, flanked by 2 weeks of near-optimal geometry. Multiple observatories worldwide coordinating intensive campaigns. Every clear night represents opportunity to gather data that might resolve current anomalies or reveal new characteristics. Late December through January, progressive fading. By year's end, magnitude drops below 13. By mid-January, below 14. Observations become challenging even for large telescopes. Spectroscopy requires longer exposures, increasing motion blur. Detailed studies become progressively harder. February 2026 and beyond, magnitude 15 or fainter. Beyond reach of all but the largest professional instruments, and even those struggle. 3-hour Atlas effectively disappears from detailed observational access, continuing outbound on its hyperbolic trajectory, eventually merging with the background noise of faint objects beyond our ability to track individually. What scientists will specifically measure. The December campaigns aren't fishing expeditions hoping to stumble upon interesting data. They're targeted investigations designed to test specific hypotheses and discriminate between competing explanations. Mass estimation refinement. The non-gravitational acceleration problem hinges partly on accurate mass. Current estimates derived from brightness, assuming typical comet albedo and density, carry uncertainty factors of 2 to 3 or more. Get the mass wrong, and outgassing thrust predictions are wrong, making the observed acceleration appear anomalous when it might not be. December observations will refine mass estimates through several approaches. First, tracking position changes over consecutive nights with high precision allows calculation of how the comet responds to gravitational forces and its own outgassing thrust. The ratio between gravitational and non-gravitational acceleration components constrains mass if you know the outgassing rate. Second, detailed coma photometry, measuring how brightness distributes across the coma rather than just total brightness, provides information about dust production rates. Dust contributes to brightness, but is lost from the nucleus permanently. Unlike gases which might recondense in shadowed regions, the amount of dust being lost, combined with observations of how coma brightness evolves, constrains how much mass the nucleus can afford to lose while maintaining observed activity levels. Third, rotation period measurements from coma morphology changes provide indirect mass constraints. Rotation rate depends on angular momentum, which relates to mass distribution. Observations through December, capturing complete rotation cycles, allow determination of period to within minutes, which combined with estimated size provides density estimates, detailed composition analysis. High-resolution spectroscopy during December will target specific questions about the comet's chemical makeup that current observations leave ambiguous. The blue coloration and near CO emission pattern need resolution. Is the spectrum truly carbon monoxide with unusual physical conditions, or is something else contributing? December observations with large telescopes. ESO's Very Large Telescope. Keck Observatory in Hawaii. Gemini telescopes will capture spectra with resolution sufficient to distinguish between CO and similar molecules, like CO2 plus CN or complex organic emissions that might mimic CO imperfectly. Water production rates currently estimated from OH emission detected by SWIFT can be refined through direct H2O observations in infrared wavelengths. Water molecules emit characteristic patterns in near-infrared around 2.7 microns, directly measuring water rather than inferring it from OH proxy measurements. Facilities equipped with infrared spectrographs will target these wavelengths specifically. Isotopic ratios, if detectable, provide clues about formation conditions. The ratio of deuterium to hydrogen DH, for example, varies depending on temperature and location during formation. Interstellar clouds show different DH ratios than solar system materials. Detecting deuterated molecules like HDO heavy water in 3I Atlas's coma would reveal whether its formation environment resembled solar system conditions or differed systematically. Trace species detection matters too. Minor molecules like methanol, formaldehyde, hydrogen sulfide, or complex organics appear in small quantities but tell stories about chemistry. Their relative abundances compared to major species like water, CO and CO2 constrain formation temperature and subsequent evolution. Structural integrity assessment. If 3I Atlas fragmented during perihelion December, observations should reveal it definitively. High-resolution imaging will search for multiple condensations, discrete bright spots in the coma indicating separated fragments, each with their own sublimation envelope. Even if fragments remain too close to resolve individually, their presence would create brightness profiles inconsistent with a single central nucleus. Coma morphology. The detailed shape and structure of the gas and dust cloud provides signatures of fragmentation. Intact comets typically show relatively symmetric comae with fan-shaped features emanating from a central point. Fragmented comets display more chaotic patterns, multiple brightness peaks, asymmetries that don't rotate consistently with a single nucleus. Brightness evolution matters too. Intact comets brighten and fade smoothly as solar distance changes. Fragmented comets show erratic brightness changes as individual pieces evolve differently, some remaining active while others deplete volatiles and fade, some experiencing delayed outbursts as newly exposed surfaces begin sublimating. Spectroscopic variations across the coma could indicate compositional differences between fragments if breakup exposed materials with different chemistry. Mapping spectra spatially. Not just observing the integrated light from the entire coma might reveal chemical inhomogeneity indicative of multiple discrete objects. Thermal emission detection. If internal heat drives unusual activity, infrared observations should detect it. Objects in space achieve equilibrium temperature, where absorbed solar radiation balances emitted infrared radiation. For a dark object at 3I Atlas's distance, equilibrium temperature should be around 200–220 Kelvin, roughly 70 to 50 Celsius. If the comet is warmer than this, it's generating internal heat or has unusual thermal properties. Infrared photometry and spectroscopy during December will measure thermal emission comparing observed temperatures to solar equilibrium values. Excess heat wouldn't prove radioactive decay. Definitively, other processes like exothermic chemical reactions could generate warmth, but it would confirm that something beyond solar heating is occurring. Conversely, finding temperatures consistent with solar equilibrium would rule out significant internal heat sources. Coordinated multi-wavelength campaigns. The December observation strategy involves coordinated campaigns across wavelengths, facilities, and observer types, maximizing information return during the brief optimal window. Optical telescopes will conduct photometry and spectroscopy in visible wavelengths, tracking brightness, color, and molecular emissions. Near-infrared facilities will target water and CO2 emissions invisible in optical wavelengths. Mid-infrared observations will measure thermal emission for temperature determination. Radio telescopes will observe at millimeter wavelengths where molecules like COHCN and methanol emit strongly, providing composition information complementary to optical spectroscopy. Radio observations aren't affected by daylight or weather, allowing around-the-clock monitoring when the comet is above the horizon. Ultraviolet observations from space-based platforms will continue tracking OH and other UV bright species. X-ray observations, though, less likely to detect signals from a comet this faint, will be attempted to search for emission from charge exchange reactions between solar wind and cometary gases. The goal is comprehensive characterization, measuring everything that can be measured during the window when measurement is possible, because after December, the opportunity vanishes. What amateur astronomers can contribute. Professional facilities operate on tight schedules allocated months or years in advance. Flexibility is limited. If weather ruins a scheduled observation night, that time is lost. If unexpected behavior demands immediate follow-up, rescheduling may be impossible. Amateur astronomers equipped with modern instruments provide valuable flexibility. When professionals are clouded out, amateurs under clear skies continue observing. When unexpected brightness changes occur between scheduled professional observations, amateurs fill the temporal gaps. Photometric monitoring, measuring brightness night after night, requires patience more than enormous telescopes. An amateur with 30-centimeter aperture and careful technique can produce measurements accurate to a few percent, contributing to the extended baseline of brightness data that reveals activity patterns. Coma morphology changes over hours as the nucleus rotates and active regions change orientation. Professional observations might capture 2 or 3 snapshots per night from a given facility. Amateurs worldwide provide near continuous coverage as Earth's rotation carries the comet across different observers' skies. This distributed network of engaged observers creates temporal resolution impossible for any single facility. The community becomes a virtual telescope array, collectively monitoring the comet with coverage approaching 24-hour continuity. To understand why 3I Atlas matters, we must place it in the broader context of interstellar object discoveries and the profound scientific questions they address. For most of human history, the possibility of detecting objects from other star systems remained theoretical. We knew such objects must exist. Gravitational interactions during planetary system formation should eject material into interstellar space regularly, but detecting them seemed impossible. They would be small, dark, moving fast through our solar system, easily mistaken for ordinary asteroids or comets if noticed at all. Then came October 19, 2017. The Pan-STARRS telescope in Hawaii detected an unusual object initially designated A2017U1. Its trajectory was wrong. Too fast, wrong shape, clearly not gravitationally bound to our sun. Within days, observations confirmed the impossible. This was an interstellar visitor. Wana Oumuamua. The first messenger. Oumuamua, Hawaiian for messenger from afar arriving first, revolutionized our understanding simply by existing. Theoretical predictions became observational reality. Interstellar objects weren't just possible, they were detectable with existing technology. But Oumuamua was strange. Its shape appeared highly elongated, cigar-like, or possibly pancake-like, with an axis ratio of at least 5:1, unusually extreme for natural objects. Its rotation was complex, tumbling rather than spinning smoothly, and it exhibited unexplained non-gravitational acceleration as it departed the inner solar system. That acceleration sparked intense debate. For most comets, non-gravitational forces come from outgassing, vaporizing ices creating thrust. But Oumuamua showed no visible coma, no tail, no obvious signs of volatile release. If it wasn't outgassing what was pushing it, conventional explanations emerged. Perhaps outgassing was occurring, but the released volatiles, maybe pure nitrogen ice or CO ice, were invisible in optical wavelengths. Perhaps the object was unusually small, making tiny amounts of outgassing sufficient to produce observed acceleration. Avi Loeb proposed an alternative. Perhaps Oumuamua was a light sail, an artificial structure pushed by solar radiation pressure. The hypothesis was controversial, criticized by many colleagues as premature speculation unsupported by evidence. But it opened a conversation about how we would recognize technology at interstellar scales, and whether we're too quick to assume everything we detect is natural. The debate revealed something important. We don't have good frameworks for distinguishing natural from artificial at cosmic scales. We've never detected confirmed extraterrestrial technology. We're making assumptions based on our technological capabilities, scaled up speculatively. If advanced civilizations exist and send probes to other stellar systems, would we recognize them? What signatures would be definitive? Oumuamua departed before these questions could be answered. We caught it late, observed, briefly lost it to distance and faintness. It left us with intriguing data, competing explanations, and a reminder that the universe contains surprises we don't always recognize immediately. Borisov, the reassuring visitor. In August 2019, amateur astronomer Gennady Borisov discovered an object that quickly showed signs of being interstellar hyperbolic trajectory, high velocity incoming from the direction of Cassiopeia. Designated 2I Borisov, with Borisov's name honored in the official designation, this second interstellar visitor arrived with better timing than Oumuamua. We detected it earlier, had months to observe as it approached and passed perihelion. And it was normal, comfortingly, reassuringly normal. 2I Borisov looked like a comet, behaved like a comet, compositionally resembled solar system comets. It had a visible coma and tail. Spectroscopy showed water, CnC2 standard cometary molecules in expected abundances. Its color was typical. Its activity level matched predictions based on size and solar distance. Non-gravitational acceleration was consistent with outgassing, without requiring exotic explanations. Detailed observations revealed it was Kuo-rich, with carbon monoxide abundance higher than typical solar system comets, but not unprecedentedly so. This hinted that interstellar comets might form in colder regions than most solar system comets, where CO ices remain stable. But the difference was quantitative rather than qualitative, a matter of degree, not kind. 2I Borisov provided the control case we needed. It demonstrated that interstellar doesn't automatically mean exotic. Some objects from other star systems apparently resemble objects from our own system because similar physical processes operate under similar conditions, regardless of location. This was scientifically valuable. It suggested cometary composition and behavior might be quasi-universal, that our understanding derived from solar system observations applies to broader galactic populations. The universe operates on consistent principles, creating similar outcomes in similar circumstances. 3I Atlas, the ambiguous case. Now comes 3I Atlas falling somewhere between Oumuamua's strangeness and 2I Borisov's conventionality. It looks like a comet, acts mostly like a comet, but exhibits quantitative anomalies that create interpretive ambiguity. It's not as obviously unusual as Oumuamua, no extreme elongation, no absence of outgassing, no immediately revolutionary characteristics. But it's not as comfortingly normal as 2I Borisov brightness. Too high acceleration, too strong spectrum, not quite matching standard molecules. This intermediate position makes 3I Atlas scientifically fascinating in different ways than its predecessors. It's testing the boundaries of natural variation, probing how much diversity exists within the category comet, asking whether our models have sufficient flexibility to accommodate the range of conditions that produce comet-like objects across the galaxy. 3 data points create a pattern more meaningful than 2. 2 points define a line, but 3 points reveal whether reality follows that line or curves away from it. Oumuamua and 2I Borisov suggested a spectrum from unusual to typical. 3I Atlas adds a 3rd point that doesn't quite fit the straight-line interpolation between them. What we're learning about interstellar populations. Each visitor teaches lessons about the diversity of objects wandering the galaxy between stars. From Oumuamua, interstellar objects can have unusual shapes and acceleration characteristics. We can't assume everything will resemble solar system objects. Natural variation includes extremes we haven't fully sampled locally. From 2I Borisov, some interstellar objects are compositionally and behaviorally similar to solar system counterparts. Similar formation processes operating in different stellar systems produce similar results. Our local understanding has broader applicability than we might have feared. From 3I Atlas, the boundary between typical and unusual is blurry. Quantitative differences, how bright, how much acceleration exactly, which molecules matter more than qualitative categories. Objects can be comet-like while retaining characteristics that challenge detailed models. Statistically, 3 objects provide minimal constraint on population properties, but they're infinitely more than 0. We're transitioning from interstellar objects are theoretical to interstellar objects are observable to interstellar objects show diversity. Future prospects. Detection capabilities are improving rapidly. The Vera Rubin Observatory, beginning science operations in 2025-2026, will conduct the legacy survey of space and time, repeatedly imaging the entire visible sky every few nights with unprecedented depth and cadence. Simulations predict Rubin might detect 1 interstellar object per year, possibly more. ESA's Comet Interceptor mission, approved for launch in the late 2020s, is designed specifically to rendezvous with a long-period comet or interstellar visitor on short notice. Unlike previous missions that targeted known objects years in advance, Interceptor will wait in space until a suitable target is discovered, then maneuver for flyby, capturing high-resolution images and in-situ measurements impossible from Earth. These improvements mean interstellar objects will transition from rare curiosities to regular discoveries. Within a decade, we might have data on dozens of visitors, enabling statistical analysis of population properties, which are comet-like. What fractions show unusual characteristics? Do patterns emerge suggesting different source populations or formation conditions? 3I Atlas occupies a crucial position in this progression. It's the 3rd visitor arriving when detection capabilities have matured beyond the surprise of Oumuamua and preparation of 2I Borisov. It's being observed more thoroughly, with better instruments, with coordinated international campaigns, applying lessons learned from previous visitors. What we learn from 3I Atlas, whether it's ultimately explained conventionally or requires expanded models, will shape how we approach the next visitor and the next, building a framework for understanding the messengers arriving from the darkness between stars. Scientific discoveries don't exist in isolation. They ripple outward, affecting adjacent fields, challenging assumptions, sometimes reshaping entire frameworks of understanding. The implications of what we learn about 3I Atlas extend far beyond one comet's characteristics. Let's explore what different explanations would mean, not just for this specific object, but for broader questions about the universe and our place within it. If the standard model proves correct. Suppose December observations resolve all anomalies within conventional comet physics. Refined mass estimates reconcile the acceleration. Detailed spectroscopy confirms the blue color as carbon monoxide with unusual but natural conditions. Brightness anomalies disappear when size and albedo are properly constrained. This outcome, the most likely scenario according to most astronomers, carries its own profound implications. First, it validates centuries of comet science. The models we've developed studying solar system comets apply to interstellar visitors formed around different stars. This suggests physical processes, ice condensation, dust, aggregation, volatile preservation, operate similarly across the galaxy. The universe is more uniform than it might be, more predictable, more amenable to understanding through local observations. Second, it demonstrates that unusual doesn't mean unprecedented. When objects exhibit characteristics outside typical ranges, our first instinct should be to explore natural variation rather than invoking exotic explanations. The lesson, nature is more diverse than our limited sampling suggests, but that diversity exists within comprehensible frameworks. Third, it reminds us that measurement uncertainties matter enormously. Parameter estimation errors, getting size or mass or composition slightly wrong cascade through calculations, making normal behavior appear anomalous. Extraordinary claims based on ambiguous data should face extraordinary skepticism until measurements improve enough to remove ambiguity. For exoplanet research, this has implications. We study planets around other stars by inference transits. That dim starlight radial velocity wobbles from gravitational tugs, sometimes direct imaging of giant planets far from their stars. We estimate planetary properties from limited data, making assumptions about composition structure, atmospheric chemistry. If our understanding of cometary physics, much simpler objects than planets, still contains significant uncertainties, how much more uncertain are exoplanet characterizations? The standard model confirmed outcome teaches humility about the limits of remote observation. It suggests we need more data, better instruments, spacecraft missions to interstellar visitors rather than just telescope observations. And it implies the universe, while full of wonders, operates on comprehensible principles, accessible to patient investigation. If fragmentation or internal heat proves correct, suppose observations confirm that 3I Atlas fragmented during perihelion or harbors internal heat sources. These unusual but natural explanations expand our models without breaking them. Fragmentation would demonstrate that interstellar comets, after millions of years, exposed to cosmic radiation and micrometeoroid impacts while traversing the galaxy, may be structurally weaker than solar system comets that formed recently, cosmically speaking, and spent less time in hostile environments. This teaches us about material evolution on million-year timescales. Processes we can't easily replicate in laboratories but can study through astronomical observation. Internal heat from radioactive decay would suggest that planetary systems forming near supernova remnants or in regions with unusual elemental abundances create objects with chemistry different from our solar system. This ties to broader questions about galactic chemical evolution. How elements synthesized in stars disperse through space, how local abundances vary, how different stellar environments produce different planetary system compositions. Both scenarios push us to expand categories. Not all comets fit into neat boxes. Some fragment easily. Some generate internal heat. Natural diversity exceeds our current taxonomies, requiring us to add subcategories. Expand models acknowledge that reality is messier than simplified frameworks suggest. For planetary science, this implies we should expect diversity in small body populations around other stars. Exoplanet systems might harbor comets with characteristics we don't see locally. Debris disks around distant stars might contain materials processed by mechanisms we haven't encountered. Our solar system is a sample size of one, and generalizing from it is risky. The lesson nature experiments continuously in billions of stellar systems across the galaxy. Most produce similar outcomes because physics constrains possibilities. But outliers exist, created by unusual local conditions. Finding those outliers teaches us about the full range of nature's creativity. If something genuinely unprecedented is occurring now, consider the most speculative possibility. December observations fail to resolve anomalies within expanded natural models. Acceleration remains unexplained by outgassing even with parameter freedom. Spectral signatures don't match any known molecular emissions despite detailed analysis. Activity patterns suggest directed rather than passive behavior. This outcome, while unlikely, would force us to confront profound questions about what we've missed. First question: Are there natural processes we haven't adequately understood or observed? Physics we've neglected because they don't appear important in solar system contexts, but matter at interstellar scales. Chemistry we haven't studied because our laboratory conditions don't replicate million-year exposure to cosmic radiation. Electromagnetic or plasma interactions we haven't modeled because they're subtle and only manifest under specific conditions. Discovering new natural processes wouldn't overturn physics, it would enrich physics by revealing phenomena occurring in regimes we haven't adequately sampled. The universe is vast, ancient, operating on scales far beyond human experience. We shouldn't be surprised if it still holds natural surprises. Second question. How do we distinguish natural from artificial at cosmic scales? If advanced technology exists, and statistically it seems likely somewhere in a galaxy with hundreds of billions of stars, what signatures would be definitive? How large would a directed thrust need to be before we could confidently distinguish it from natural outgassing? How regular would signal modulation need to be before ruling out natural emission? How geometric would structures need to be before excluding natural formation? These aren't philosophical questions, they're methodological challenges with practical implications for how we interpret observations. The universe might contain technology we don't recognize as such because our pattern matching evolved for human-scale terrestrial contexts, not cosmic scales. Third question. What's our burden of proof for extraordinary claims? Science demands rigor. Extraordinary claims require extraordinary evidence. But how much evidence is sufficient if every individual measurement has conventional explanation, but the pattern of measurements seems improbable under natural assumptions? At what point does skepticism of exotic hypotheses become more forced than skepticism of conventional ones? This epistemological question has no simple answer. Different scientists draw lines differently based on training, field experience, philosophy of science, and sometimes temperament. Conservative scientists emphasize avoiding false positives, don't claim discoveries that aren't real. Liberal scientists emphasize avoiding false negatives, don't miss genuine discoveries through excessive skepticism. Both positions have merit. Philosophical implications. Beyond technical questions, 3i Atlas touches deeper issues about humanity's place in the cosmos. If interstellar visitors are all natural, if life and intelligence are rare in the galaxy, we confront profound loneliness. The universe is vast, ancient, yet apparently barren of other minds contemplating existence. This suggests intelligence is either extremely unlikely or extremely short-lived. Neither conclusion is comforting. If signs of technology exist but we fail to recognize them, we confront our perceptual limitations. How much of reality do we miss because our instruments can't detect it or our minds can't conceptualize it? Are we like medieval scholars, trying to understand radio waves, lacking the basic framework to even ask the right questions? If life and technology are common, but we've detected no unambiguous evidence, we confront the Fermi paradox in acute form. Where is everybody? Why haven't we found clear proof, despite decades of searching? Are we not looking correctly? Are we looking at the wrong places or times? Is interstellar travel impractical, even for advanced civilizations? Do civilizations routinely self-destruct before achieving interstellar capability? These questions extend beyond astronomy into philosophy, sociology, anthropology. They ask not just, what is 3i Atlas, but what does its nature tell us about the distribution of matter, energy, and complexity in the universe? The value of mystery. Regardless of ultimate conclusions about 3i Atlas, the journey of investigation has value, independent of destination. Scientific method at its best operates through the tension between data and theory, observation and explanation, conservatism and openness. We collect evidence, carefully interpret it, rigorously consider alternatives. fairly proportion belief to evidence strength and remain willing to revise conclusions when new data demand it. 3i Atlas exemplifies this process. We have observations that challenge standard models without definitively refuting them. We have competing explanations, each with strengths and weaknesses. We're gathering more data to discriminate between hypotheses. We're arguing civilly based on evidence about how to interpret ambiguous measurements. This is science in action, not the sanitized textbook version, where answers are obvious and methods are straightforward, but the messy, uncertain, deeply human process of trying to understand reality despite limited information and imperfect instruments. The mystery itself has value. It drives investigation, sparks creativity, forces us to question assumptions, reminds us that certainty is rare and provisional. The discomfort of not knowing, of having questions without immediate answers, is intellectually honest acknowledgement that the universe doesn't owe us easy understanding. When 3i Atlas fades from view, when December observations are analyzed and papers published, we'll understand more than we do now. Whether that understanding resolves into comfortable explanation or uncomfortable persistent anomaly, we'll have learned something true about an interstellar visitor's journey through our cosmic neighborhood, and will be better prepared for the next messenger arriving from darkness. We stand now in mid-November 2025, roughly 1 month away from 3i Atlas's closest approach to Earth, 1 month from the optimal observation window that will determine whether this interstellar visitor reveals its nature or departs still shrouded in mystery. What do we know with certainty? 3i Atlas is the third confirmed interstellar object in human history, a visitor from beyond our solar system following a hyperbolic path that will carry it back to the void. It exhibited non-gravitational acceleration documented by NASA. It brightened unexpectedly beyond standard predictions. It displays blue coloration with spectral signatures close to but not perfectly matching carbon monoxide. Multiple independent institutions confirmed these observations. They are real measurements, not artifacts or errors. What remains uncertain: whether conventional comet models with adjusted parameters fully explain these observations, whether fragmentation, internal heat, or other natural processes created the anomalies, whether December observations will resolve mysteries or deepen them. What happened during those 3 invisible days behind the sun? The value of uncertainty lies not in its comfort. Uncertainty is uncomfortable, but in its honesty. Science doesn't always provide immediate answers. Some questions require patience, accumulation of evidence, elimination of competing hypotheses through careful observation. What we're witnessing with 3i Atlas is science in process. Not definitive conclusions packaged for easy consumption, but genuine investigation unfolding in real time. The uncertainty, the competing explanations, the need for more data. This is what actual science looks like away from textbooks and popularized narratives. We live in extraordinary time. The first generation of humans capable of systematically studying objects from other star systems. Each visitor teaches different lessons about cosmic diversity, about the range of conditions under which matter coalesces and evolves, about the universe beyond our small corner of one galaxy. Whether 3i Atlas ultimately proves to be an unusual but natural comet, an object requiring expanded models, or something genuinely unprecedented, we learn. The investigation itself advances understanding regardless of specific conclusions. December 19th approaches. Between now and then, telescopes worldwide will track this faint, distant object. Observations will accumulate. Analyses will refine. Understanding will hopefully emerge. And when 3i Atlas fades from view in early 2026, continuing its journey back to the darkness between stars, we will watch it depart, either with answers or with better questions. Either outcome serves science. The universe keeps its secrets carefully. Sometimes it shares them, sometimes it only hints, and sometimes it leaves us wondering whether we asked the right questions at all. What will December reveal? We wait, we watch, we listen to what the cosmos whispers in wavelengths of light across millions of miles of emptiness. And perhaps, if we're attentive enough, we'll hear something true. The sky has more to tell us. And this visitor born in darkness, traveling for millennia, gracing our small system briefly, before returning to the infinite, carries messages we're only beginning to learn how to read.